Hey guys, welcome back to another episode of my channel. My name is Keika. I'll be going over textbooks chapter by chapter, section by section. And in this video, we'll be going over concept 3.3. Acidic and basic conditions affect living organisms. Okay. Occasionally, a hydrogen atom participating in a hydrogen bond between two water molecules shifts from one molecule to the other. When this happens, the hydrogen atom leaves its electron behind, and what is actually transferred is a hydrogen ion, a single proton with a charge of +1. The water molecule that lost a proton is now a hydroxide ion, which has a charge of -1. The proton binds to the other water molecule, making that molecule a hydronium ion, H3O+. We can picture the chemical reactions as it follows. So as we can see here, we see two hydrogen ions, as noted here, two H2O, noting two water molecules, And then this is a reversible reaction, meaning it can go both ways. And it forms hydronium, which has 3 hydrogens and 1 oxygen, and a hydroxide, which is an oxygen and a hydrogen anion. So yes. By convention, H hydrogen ions is used to represent H3O, the hydronium ion, and we follow that practice in this book. Keep in mind though that the hydrogen ions do not exist on its own in an aqueous solution. It is always associated with a water molecule in the form of H3O, hydronium. As indicated by the double arrows, this is a reversible reaction that reaches a state of dynamic equilibrium when water molecules dissociate at the same rate that they are being reformed from hydrogen ions to hydroxide ions. At this equilibrium point, the concentration of water molecules greatly exceeds the concentrations of hydrogen ions and hydroxide ions. In pure water, the only one water molecule in every 554 million is dissociated. The concentration of hydrogen ions and hydroxide ions in pure water is therefore 10 to the -7th molarity at 25 degrees Celsius. This means there is only 1/10,000,000th of a mole of hydrogen ions per liter of pure water, and an equal number of hydroxide ions. Even so, this is a huge number, over 60 trillion of each ion in a liter of pure water. Although the dissociation of water is reversible and statistically rare, it is exceedingly important in the chemistry of life. Hydrogen ions and hydroxide ions are very reactive. Changes in their concentration can drastically affect a cell's protein and other complex molecules. As we have seen, the concentrations of hydrogen ions and hydroxide ions are equal in pure water, but adding certain kinds of solutes, such as called acids and bases, disrupts this balance. Biologists use something called the pH scale to describe how acidic or basic, the opposite of acidic, a solution is. In the remainder of this chapter, you will learn about acids, bases, and pH, and why changes in pH can adversely affect organisms. So, I explained a little bit of what they wrote here. So I wrote, occasionally hydrogen atoms leaves an electron behind, and what's transferred is a hydrogen ion. Water molecule that lost a proton is now a hydroxide ion. Proton binds to other water molecule, making hydronium ion. Okay. So hydrogen ions, H+, is used to represent hydronium, H3O+. So technically it's supposed to be H3O plus when they're referring to a liquid or a solution of water, but they just use H plus to make it easier. But technically it's H3O because H plus hydrogen ions do not exist on its own in an aqueous solution. It is always associated with a water molecule as H3O plus. This is a reversible reaction that reaches a state of dynamic equilibrium when water molecules dissociate at the same rate they are being formed, from H plus to OH minus, from hydrogen ions to hydroxide ions. At equilibrium, concentration of water molecules greatly exceeds the concentrations of H plus and OH minus. In pure water, only one water molecule in every 554 million is dissociated. So the concentration of H plus and OH minus in pure water is therefore 10 to the negative 7th m, or molarity. So this part here, in pure water, only one water molecule in every 554 million is dissociated. I'm trying to wrap my mind around what this means. I'm not sure myself. So dissociation is when they separate. So when you get a hydrogen ion and a hydroxide ion. So that's dissociation, when they separate into two different ions. So only one water molecule separates into hydrogen and hydroxide every 554 million times. 1 out of 554 million. And that's in pure water. That's interesting to know. Okay, moving on. Acids and bases. What would cause an aqueous solution to have an imbalance of H plus and OH minus concentrations? When acids dissolve in water, they donate an additional hydrogen ion to the solution. An acid is a substance that increases the hydrogen ion concentration of a solution. For example, when hydrochloric acid is added to water, hydrogen ions dissociate from chloride ions. So when hydrochloric acid is added to water, the hydrogen from the hydrochloric acid separates itself from the chloride ion, and it becomes an ion. Okay. The source of H plus, dissociation of water is the other source, results in an acidic solution, one having more hydrogen ions than hydroxide. A substance that reduces the hydrogen ion concentration of a solution is called a base. Some bases reduce the hydrogen ion concentration directly by accepting hydrogen ions. Ammonia, for instance, acts as a base when the unshared electrons pair in nitrogen's valence shell attracts. Ammonia, for instance, acts as a base when the unshared electron pair in nitrogen's valence shell attracts a hydrogen ion from the solution, resulting in ammonium ion. Okay. Other bases reduce the hydrogen ion? Hydrogen ion, right? Yeah, hydrogen ion. Other bases reduce the hydrogen ion concentration indirectly by dissociating to form hydroxide ions, which combine with hydrogen ions and form water. One such base is sodium hydroxide, which in water dissociates into ions. So we see sodium hydroxide separating or dissociating into a sodium ion and a hydroxide ion. hydroxide ion. In either case, the base reduces the hydrogen ion concentration. Solutions with a higher concentration of hydroxide than hydrogen ions are known as basic solutions. A solution in which the hydrogen ions and hydroxide ion concentration are equal is said to be neutral. Notice that single arrows were used in the reactions for hydrochloride hydrochloric acid. The single arrows were used in reactions for hydrochloric acid and sodium hydroxide. These compounds dissociate completely when mixed with water, so hydrochloric acid is called a strong acid and sodium hydroxide a strong base. In contrast, ammonia is a weak base. The double arrows in the reaction for ammonia indicate that the binding and release of hydrogen ions are reversible reactions, although at equilibrium there will be a fixed ratio of NH4 plus to NH3. Weak acids are acids that reversibly release and accept back hydrogen ions. An example is carbonic acid. So we see carbonic acid dissociating into bicarbonate ion and hydrogen ion. Here, the equilibrium so favors the reaction in the left direction, that when carbonic acid is added to pure water, only 1% of the molecules are dissociated at a particular time. Still, that is enough to shift the balance of hydrogen ions and hydroxide ions from neutrality. Only 1% of the molecules are dissociated at any particular time. That's pretty slow. So for acids and bases, I wrote, when acids dissolve in water, they donate additional H plus to the solution. Acid is a substance that increases the hydrogen ion concentration of a solution. So hydrochloric acid added to water results in hydrogen ions dissociated from chloride ions. So HCl turns into H plus Cl minus. Base is a substance that reduces the hydrogen ion concentration of a solution, sometimes by accepting hydrogen ions, such as ammonia, where they accept a hydrogen ion to create ammonium, and sometimes they dissociate to form, or sometimes by dissociating to form hydroxide, which combines with water to form, sometimes by dissociating to form hydroxide, which combines with hydrogen and forms water. Sodium hydroxide dissociates to sodium ion and hydroxide ion. A solution in which hydroxide ions and hydrogen ions concentrations are equal is said to be neutral. Strong acids and bases tend to dissociate completely in water. Ammonia is a weak base, allowing it to have double arrows in the reaction, and it indicates that the binding and release of hydrogen ions are reversible reactions, although there will be fixed ratios of NH4 plus and NH3 at equilibrium. So, weak acids are acids that reversibly release and accept back hydrogen ions. For example, would be carbonic acid and H2CO3. H2CO3. Oh, that's carbonic acid, yes. Okay. The pH scale. In any aqueous solution at 25 degrees Celsius, the product of hydrogen ions and hydroxide concentrations is constant at 10 to the negative 14th. This can be written here, H plus multiplied by hydroxide is equal to 10 to the negative 14th. The brackets indicate molar concentration. As previously mentioned, in a neutral solution at 25 degrees Celsius, hydrogen ions is equal to 10 to the negative 7th, and hydroxide ions are equal to 10 to the negative 7th as well. Therefore, the product of hydrogen ions and hydroxide ions in a neutral solution at 25 degrees Celsius is 10 to the negative 14th. If enough acid is added to a solution to increase hydrogen ions to 10 to the negative 5 molarity, then hydroxide will decline by an equivalent factor of 10 to the negative 9th molarity. This constant relationship expresses the behavior of acids and bases in an aqueous solution. An acid not only adds hydrogen ions to a solution, but also removes hydroxide ions because of the tendency for hydrogen ions to combine with hydroxide ions, forming water. A base has the opposite effect, increasing hydroxide concentration but also reducing hydrogen concentration by the formation of water. If enough of a base is added to raise the hydroxide concentration of 10 to the negative 4th molarity, it will cause the hydrogen ion concentration to drop to 10 to the negative 10th molarity. Whenever we know the concentration of either hydrogen ions or hydroxide ions in an aqueous solution, we can deduce the concentration of the other ion. The pH scale is a simple numerical method for expressing the range of hydrogen ion concentrations. The hydrogen ion concentrations of solutions can vary by a factor of 100 trillion or more. Instead of using moles per liter, the pH scale compresses the range of hydrogen ion concentrations by employing logarithms. In pH, the pH of a solution is defined as the negative logarithm, base 10, of the hydrogen ion concentration. So pH equals negative log hydrogen ion. And here we have a scale of examples of the pH scale and the pH values. So for examples of basic solutions, we have oven cleaner, bleach, ammonia, magnesia. Neutral would be seawater, human blood, tears, pure water, saliva, urine. These are classified as neutral. Rainwater is also neutral. On the acidic side, we have battery acid, gastric juice, lemon juice, vinegar, wine, cola, formic acid from ants, tomato juice, beer, and black coffee. For a neutral aqueous solution, hydrogen ion concentration is 10 to the negative 7th molarity, giving us negative log 10 to the negative 7th equals negative 7. Negative 1 times negative 7 equals 7. Notice that pH decreases as hydrogen ion concentration increases. Notice too that although the pH scale is based on hydrogen ion concentration, it also implies hydroxide concentration. A solution of pH 10 has a hydrogen ion concentration of 10 to the negative 10th molarity, and the hydroxide ion concentration of 10 to the negative 4th molarity. The pH of a neutral aqueous solution at 25 degrees Celsius is 7, the midpoint of the pH scale. A pH value less than 7 denotes an acidic solution. The lower the number, the more acidic the solution. The pH for basic solutions is above 7. Most biological fluids, such as blood and saliva, are within the range of 6 to 8. There are a few exceptions, however. including the strongly acidic digestive juice of the human stomach, gastric juice, which has a pH of about 2. Remember that each pH unit represents a 10-fold difference in hydrogen ion and hydroxide concentrations. It is this mathematical feature that makes the pH scale so compact. A solution of pH 3 is not twice as acidic as a solution of pH 6, but 1,000 times more acidic. When the pH of a solution changes slightly, the actual concentration of hydrogen ions and hydroxide ions in the solution changes substantially. So for pH scale, this was a little confusing to read, but I think I made sense of it. In any aqueous solution at 25 degrees Celsius, the product of hydrogen ions and hydroxide ions is constant at 10 degrees, or 10 to the negative 14th. So hydrogen ions and hydroxide ions equal 10 to the negative 14th. In a neutral solution at 25 degrees Celsius, hydrogen ions equal 10 to the negative 7th, and hydroxide ions equal 10 to the negative 7th. The product of hydrogen ions and hydroxide ions in a neutral solution at 25 degrees Celsius is 10 to the negative 14th. An acid not only adds hydrogen ions to a solution, but also removes hydroxide ions because of the tendency for hydrogen ions to combine with hydroxide ions, forming water. Base has the opposite effect. It increases hydroxide concentration by reducing hydrogen concentration by formation of water. Whenever we know the concentration of either hydrogen ions or hydroxide ions in an aqueous solution, we can deduce the concentration of the other ion. The pH scale is a simple numerical method for expressing the range of hydrogen ion concentration. The pH of a solution is defined as the negative logarithm base 10 of the hydrogen ion concentration. And I put the pH equals negative log hydrogen ion. For a neutral aqueous solution, hydrogen ion concentration is 10 to the negative 7th molarity, giving us negative log 10 to the negative 7th equals negative 1 times negative 7 equals 7. pH decreases as hydrogen ion concentration increases. Although pH scale is based on hydrogen concentration, hydroxide is implied. A solution for pH 10 has a concentration ion. A solution of pH 10 has a hydrogen ion concentration of 10 to the negative 10th molarity and a hydroxide ion concentration of 10 to the negative 4th molarity. So that doesn't really add up to me. Solution of 10 pH has a hydrogen ion concentration of 10 to the negative 10 m. So shouldn't it be acidic? No. The hydrogen concentration. Oh, it's negative. It's a negative logarithm. So yeah. Hold on. So this part confuses me. If you guys can understand, because I'm thinking that the pH 10 implies a basic solution, because pH decreases as hydrogen ion concentration increases. Maybe they switched it. Maybe they mean hydroxide. Concentration is 10 to the negative 10th molarity. I don't think they'd make that mistake, though. You know what? I'm just going to skip over this. But if you guys understand what I'm trying to say, can you please explain it to me in the comment section below? Thank you. Now moving on. Buffers. The internal pH of most living cells is close to 7. Even a slight change in pH can be harmful because of the chemical processes of the cell. Even a slight change in pH can be harmful because the chemical processes in a cell are very sensitive to the concentrations of hydrogen and hydroxide ions. The pH of human blood is very close to 7.4, which is slightly basic. A person cannot survive for more than a few minutes if the blood pH drops to 7 or rises to 7.8. And a chemical system exists in the blood that maintains a stable pH. If 0.01 mole of a strong acid is added to a liter of pure water, the pH drops from 7.0 to 2.0. The pH drops from 7.0 to 2.0. If the same amount of acid is added to a liter of blood, however, the pH decrease is only from 7.4 to 7.3. Why does the addition of acid have so much less effect on the pH of blood than it does on the pH of water? The presence of substances called buffers allow biological fluids to maintain a relatively constant pH despite the addition of acids or bases. A buffer is a substance that minimizes changes in the concentrations of hydrogen and hydroxide ions in the solution. It does so by accepting hydrogen ions from the solution when they are in excess and donating hydrogen ions to the solution when they have been depleted. Most buffer solutions contain a weak acid and its corresponding base, which combine reversibly with hydrogen ions. Several buffers contribute to pH stability in human blood and many other biological solutions. One of these is carbonic acid, which is formed when carbon dioxide reacts with water in blood plasma. As mentioned earlier, carbonic acid dissociates to yield a bicarbonate ion and a hydrogen ion. The chemical equilibrium between carbonic acid and bicarbonate acts as a pH regulator, the reaction shifting left or right as processes in the solution add or remove hydrogen ions. If hydrogen ion concentration in blood begins to fall, that is, if pH rises, the reaction proceeds to the right and more carbonic acid dissociates, replenishing hydrogen ions. But when the hydrogen ion concentration in blood begins to rise, when pH drops, the reaction proceeds to the left, with bicarbonate with HCO3, the base, removing the hydrogen ions from the solution and forming H2CO3. Thus, the carbonic acid bicarbonate buffering system consists of an acid and a base in equilibrium with each other. Most other buffers are also acid-base pairs. Okay, so buffers. The internal pH of most living cells is close to 7. Even a slight change in pH can be harmful because the chemical processes of the cell are very sensitive to the concentrations of hydrogen and hydroxide ions. pH of human blood is 7.4, very slightly basic. A person cannot survive for more than a few minutes if blood pH drops to 7 or rises to 7.8. So you have a range of 0.4. Buffer is a substance that minimizes changes in concentrations of hydrogen ion and hydroxide ion concentration in the solution. Allows biological fluids to maintain a relatively constant pH despite the addition of acids or bases. Accepts hydrogen ions when they are in excess and donates hydrogen ions when they have been depleted. Most buffer solutions contain a weak acid and its corresponding base, which combine reversibly with hydrogen ions. Several buffers contribute to pH stability. Carbonic acid formed when CO2 reacts with water in blood plasma. Carbonic acid dissociates to yield bicarbonate ion and hydrogen ion. The chemical equilibrium between carbonic acid and bicarbonate acts as a pH regulator, the reaction shifting left or right as other processes in the solution adds or removes hydrogen ions. The carbonic acid bicarbonate buffering system consists of an acid and a base in equilibrium with each other. Acidification, a threat to our oceans. Among the many threats to water quality posed by human activities is the burning of fossil fuels, which releases carbon dioxide into the atmosphere. The resulting increase in atmospheric carbon dioxide levels has caused global warming and other aspects of climate change. In addition, about 25% of human-generated carbon dioxide is absorbed by the oceans. In spite of the huge volume of water in the oceans, scientists worry that the absorption of so much carbon dioxide will harm marine ecosystems. Recent data have shown that such fears are well-founded. When carbon dioxide dissolves in seawater, it reacts with water to form carbonic acid, which lowers ocean pH. This process, known as ocean acidification, alters the delicate balance of conditions for life in the oceans. Based on measurements of carbon dioxide levels in air bubbles trapped in the ice over thousands of years, scientists calculate that the pH of the oceans is 0.1 pH unit lower, more acidic now than at any time in the past 420,000 years ago. Recent studies predict that it will drop another 0.3 or 0.5 pH unit by the end of the century. That's huge. Because just for reference, they said that the pH of human blood is 7.4, and if it drops 0.4 to 7, or rises to 7.8, which is an additional 0.4, a person cannot survive. That's by 0.4 of a degree, right? So if it drops 0.3 to 0.5 pH unit by the end of the century, well, who knows what kind of changes there will be. As seawater acidifies, the extra hydrogen ions combine with carbonate ions to form bicarbonate ions, thereby reducing the carbonate ion concentration. Scientists predict that ocean acidification will cause the carbonate ion concentration to decrease by 40% by the year 2100. This is of great concern because carbonate ions are required for calcification, the production of calcium carbonate, by many marine organisms, including reef-building corals and animals that build shells. The scientific skills review exercise allows you to work with data from an experiment examining the effect of carbonate ion concentration on coral reefs using an artificial system. In 2018, researchers carried out the first carbon dioxide enhancement study on an unconfined natural coral reef, observing that addition of carbon dioxide suppressed calcification and concluding that ocean acidification is likely to cause profound ecosystem-wide changes in coral reefs. Coral reefs are sensitive ecosystems that act as havens for a great diversity of marine life. The disappearance of coral reef systems would be a tragic loss to biological diversity. Is there any reason for optimism about the future quality of water resources on our planet? It is that we have made progress in learning about the delicate chemical balances in oceans, lakes, and rivers. Continued progress can only come from the actions of informed individuals like yourselves who are concerned about environmental quality. This requires understanding the crucial role that water plays in the suitability of the environment for continued life on Earth. So, acidification, a threat to our oceans. Among the many threats to water quality posed by human activities is the burning of fossil fuels, which releases carbon dioxide into the atmosphere. 25% of human-generated carbon dioxide is absorbed by the oceans. When carbon dioxide dissolves in seawater, carbonic acid forms, which lowers ocean pH. Ocean acidification alters the balance of conditions for marine ocean life. Decreased carbonate ion concentration may affect reef-building corals or animals that build shells. The disappearance of coral reef ecosystems would be a tragic loss to biological diversity. Alright. So, you guys, we have finished Chapter 3, Water and Life. So, just to quickly go over everything that we've been through. We went through Concept 3.1, polar covalent bonds in water result in hydrogen bonding. Concept 3.2, 4 emergent properties of water contribute to Earth's suitability for life. And Concept 3.3 just now, acidic and basic conditions affect living organisms. Okay, so next video we'll be going over Chapter 4, Carbon and the Molecular Diversity of Life. Okay, so I hope you guys enjoyed this video and that you learned a lot. This was kind of a tough one for me, but we got through it, and I'm sure if I read it over again, I'll understand, or even if I just do a quick search on Ecosia or something, then I'll understand it a little bit better. But the text is doing a pretty good job at explaining everything in a way that makes sense. I hope you guys feel the same way. And don't forget to like, subscribe, and I'll see you guys next time. Bye.